A supercapacitor is a high-capacity electrochemical capacitor with capacitance values much higher than other capacitors that bridge the gap between electrolytic capacitors and rechargeable batteries. They typically store 10 to 100 times more energy per unit volume or mass than electrolytic capacitors, can accept and deliver charge much faster than batteries, and tolerate many more charge in discharge cycles than rechargeable batteries. They are however 10 times larger than conventional batteries for a given charge. Supercapacitors are used in applications requiring many rapid charge-discharge cycles rather than long-term compact energy storage. Within cars, buses, trains, cranes and elevators, where they are used for regenerative braking, short-term energy storage or burst mode power delivery. Smaller units are used as memory backup for static random access memory. Supercapacitors do not use the conventional solid dielectric of ordinary capacitors. They use electrostatic double-layer capacitance or electrochemical pseudo-capacitance or a combination of both instead. Electrostatic double-layer capacitors use carbon electrodes or derivatives with much higher electrostatic double-layer capacitance than electrochemical pseudo-capacitance, achieving separation of charge in a Helmholtz double layer at the interface between the surface of a conductive electrode and an electrolyte. The separation of charge is of the order of a few angstroms, much smaller than in a conventional capacitor. Electrochemical pseudocapacitors use metal oxide or conducting polymer electrodes with a high amount of electrochemical pseudocapacitance. Pseudocapacitance is achieved by Faradaic electron charge transfer with redox reactions, intercalation or electrosorption. Hybrid capacitors, such as the lithium-ion capacitor, use electrodes with differing characteristics, one exhibiting mostly electrostatic capacitance and the other mostly electrochemical capacitance. The electrolyte forms a conductive connection between the two electrodes which distinguishes them from electrolytic capacitors where the electrolyte is the second electrode. Supercapacitors are polarized by design with asymmetric electrodes, or, for symmetric electrodes, by a potential applied during manufacture. History. Development of the double-layer and pseudocapacitance models. Evolution of components. In the early 1950s, General Electric engineers began experimenting with porous carbon electrodes in the design of capacitors, from the design of fuel cells and rechargeable batteries. Activated charcoal is an electrical conductor that is an extremely porous, spongy form of carbon with a high specific surface area. In 1957, H. Becker developed a low-voltage electrolytic capacitor with porous carbon electrodes. He believed that the energy was stored as a charge in the carbon pores as in the pores of the etched foils of electrolytic capacitors. Because the double-layer mechanism was not known by him at the time, he wrote in the patent, "It is not known exactly what is taking place in the component if it is used for energy storage, but it leads to an extremely high capacity." General Electric did not immediately pursue this work. In 1966, researchers at Standard Oil of Ohio developed another version of the component as electrical energy storage apparatus, while working on experimental fuel cell designs. The nature of electrochemical energy storage was not described in this patent. Even in 1970, the electrochemical capacitor patented by Donald L. Booz was registered as an electrolytic capacitor with activated carbon electrodes. Early electrochemical capacitors used two aluminum foils covered with activated carbon, the electrodes, which were soaked in an electrolyte and separated by a thin porous insulator. This design gave a capacitor with a capacitance on the order of 1 farad, significantly higher than electrolytic capacitors of the same dimensions. This basic mechanical design remains the basis of most electrochemical capacitors. SOHIO did not commercialize their invention, licensing the technology to NEC, who finally marketed the results as supercapacitors in 1971. to provide backup power for computer memory. Between 1975 and 1980, Brian Evans Conway conducted extensive fundamental and development work on ruthenium oxide electrochemical capacitors. In 1991, he described the difference between supercapacitor and battery behavior in electrochemical energy storage. In 1999, he coined the term supercapacitor to explain the increased capacitance by surface redox reactions with Faradaic charge transfer between electrodes and ions. His supercapacitor stored electrical charge partially in the Helmholtz double layer and partially as a result of Faradaic reactions with pseudo-capacitance, charge transfer of electrons and protons between electrode and electrolyte. The working mechanisms of pseudo-capacitors are redox reactions, intercalation and electrosorption. With his research, Conway greatly expanded the knowledge of electrochemical capacitors. The market expanded slowly. That changed around 1978 as Panasonic marketed its Gold Caps brand. This product became a successful energy source for memory backup applications. Competition started only years later. In 1987, Elner Dynacap S entered the market. First-generation EDLCs had relatively high internal resistance that limited the discharge current. They were used for low-current applications such as powering SRAM chips or for data backup. At the end of the 1980s, improved electrode materials increased capacitance values. At the same time, the development of electrolytes with better conductivity lowered the equivalent series resistance, increasing discharge currents. The first supercapacitor with low internal resistance was developed in 1982 for military applications through the Pinnacle Research Institute, and were marketed under the brand name ultracapacitor. In 1992, Maxwell Laboratories took over this development. Maxwell adopted the term ultracapacitor from Pre and called them boost caps to underline their use for power applications. Since capacitors' energy content increases with the square of the voltage, researchers were looking for a way to increase the electrolyte's breakdown voltage. In 1994, using the anode of a 200V high-voltage tantalum electrolytic capacitor, They, Evans developed an electrolytic hybrid electrochemical capacitor. These capacitors combine features of electrolytic and electrochemical capacitors. They combine the high dielectric strength of an anode from an electrolytic capacitor with the high capacitance of a pseudocapacitive metal oxide cathode from an electrochemical capacitor, yielding a hybrid electrochemical capacitor. Evans's capacitors, coined Capatry, had an energy content about a factor of 5 higher than a comparable tantalum electrolytic capacitor of the same size. Their high costs limited them to specific military applications. Recent developments include lithium-ion capacitors. These hybrid capacitors were pioneered by FDK in 2007. They combine an electrostatic carbon electrode with a pre-doped lithium-ion electrochemical electrode. This combination increases the capacitance value. Additionally, the pre-doping process lowers the anode potential and results in a high cell output voltage, further increasing energy density. Research departments are active in many companies, and universities are working to improve characteristics such as energy density, power density, cycle stability, and reduce production costs. Basics. Basic design. Electrochemical capacitors consist of two electrodes separated by an ion-permeable membrane, and an electrolyte ionically connecting both electrodes. When the electrodes are polarized by an applied voltage, ions in the electrolyte form electric double layers of opposite polarity to the electrode's polarity. For example, positively polarized electrodes will have a layer of negative ions at the electrolyte interface along with a charge balancing layer of positive ions adsorbing onto the negative layer. The opposite is true for the negatively polarized electrode. Additionally, depending on electrode material and surface shape, Some ions may permeate the double layer, becoming specifically adsorbed ions, and contribute with pseudo-capacitance to the total capacitance of the supercapacitor. Capacitance distribution. The two electrodes form a series circuit of two individual capacitors C1 and C2. The total capacitance C total is given by the formula. Supercapacitors may have either symmetric or asymmetric electrodes. Symmetry implies that both electrodes have the same capacitance value, yielding a total capacitance of half the value of each single electrode. For asymmetric capacitors, the total capacitance can be taken as that of the electrode with the smaller capacitance. Storage principles. Electrochemical capacitors use the double layer effect to store electric energy. However, this double layer has no conventional solid dielectric to separate the charges. There are two storage principles in the electric double layer of the electrodes that contribute to the total capacitance of an electrochemical capacitor. Double layer capacitance, electrostatic storage of the electrical energy achieved by separation of charge in a Helmholtz double layer. Pseudo-capacitance, electrochemical storage of the electrical energy achieved by Faradaic redox reactions with charge transfer. Both capacitances are only separable by measurement techniques. The amount of charge stored per unit voltage in an electrochemical capacitor is primarily a function of the electrode size, although the amount of capacitance of each storage principle can vary extremely. Practically, these storage principles yield a capacitor with a capacitance value in the order of 1 to 100 farad. Electrostatic double-layer capacitance. Every electrochemical capacitor has two electrodes, mechanically separated by a separator, which are ionically connected to each other via the electrolyte. The electrolyte is a mixture of positive and negative ions dissolved in a solvent such as water. At each of the two electrode surfaces originates an area in which the liquid electrolyte contacts the conductive metallic surface of the electrode. This interface forms a common boundary among two different phases of matter, such as an insoluble solid electrode surface and an adjacent liquid electrolyte. In this interface occurs a very special phenomenon of the double layer effect. Applying a voltage to an electrochemical capacitor causes both electrodes in the capacitor to generate electrical double layers. These double layers consist of two layers of charges. One electronic layer is in the surface lattice structure of the electrode, and the other, with opposite polarity, emerges from dissolved and solvated ions in the electrolyte. The two layers are separated by a monolayer of solvent molecules. G, for water as solvent, by water molecules, called inner Helmholtz plane. Solvent molecules adhere by physical adsorption on the surface of the electrode and separate the oppositely polarized ions from each other, and can be idealized as a molecular dielectric. In the process, there is no transfer of charge between electrode and electrolyte, so the forces that cause the adhesion are not chemical bonds but physical forces. The adsorbed molecules are polarized, but, due to the lack of transfer of charge between electrolyte and electrode, suffered no chemical changes. The amount of charge in the electrode is matched by the magnitude of countercharges in outer Helmholtz plane. This double-layer phenomena store electrical charges as in a conventional capacitor. The double-layer charge forms a static electric field in the molecular layer of the solvent molecules in the IHP that corresponds to the strength of the applied voltage. The double layer serves approximately as the dielectric layer in a conventional capacitor, albeit with the thickness of a single molecule. Thus, the standard formula for conventional plate capacitors can be used to calculate their capacitance. Accordingly, capacitance C is greatest in capacitors made from materials with a high permittivity epsilon, large electrode plate surface areas A, and small distance between plates D. As a result, double-layer capacitors have much higher capacitance values than conventional capacitors. arising from the extremely large surface area of activated carbon electrodes and the extremely thin double-layer distance on the order of a few angstroms. The main drawback of carbon electrodes of double-layer SCs is small values of quantum capacitance which act in series with capacitance of ionic space charge. Therefore, further increase of density of capacitance in SCs can be connected with increasing of quantum capacitance of carbon electrode nanostructures. The amount of charge stored per unit voltage in an electrochemical capacitor is primarily a function of the electrode size. The electrostatic storage of energy in the double layers is linear with respect to the stored charge, and correspond to the concentration of the adsorbed ions. Also, while charge in conventional capacitors is transferred via electrons, capacitance in double-layer capacitors is related to the limited moving speed of ions in the electrolyte and the resistive porous structure of the electrodes. Since no chemical changes take place within the electrode or electrolyte, charging and discharging electric double layers in principle is unlimited. Real supercapacitors' lifetimes are only limited by electrolyte evaporation effects. Electrochemical pseudocapacitance applying a voltage at the electrochemical capacitor terminals moves electrolyte ions to the opposite polarized electrode and forms a double layer in which a single layer of solvent molecules acts as separator. Pseudocapacitance can originate when specifically adsorbed ions out of the electrolyte pervade the double layer. This pseudocapacitance stores electrical energy by means of reversible Faradaic redox reactions on the surface of suitable electrodes in an electrochemical capacitor with an electric double layer. Pseudocapacitance is accompanied with an electron charge transfer between electrolyte and electrode coming from a desolvated and adsorbed ion, whereby only one electron per charge unit is participating. This Faradaic charge transfer originates by a very fast sequence of reversible redox, intercalation or electrosorption processes. The adsorbed ion has no chemical reaction with the atoms of the electrode since only a charge transfer takes place. The electrons involved in the Faradaic processes are transferred to or from valence electron states of the redox electrode reagent. They enter the negative electrode and flow through the external circuit to the positive electrode where a second double layer with an equal number of anions has formed. The electrons reaching the positive electrode do not transfer to the anions forming the double layer. Instead, they remain in the strongly ionized and electron-hungry transition metal ions of the electrode's surface. As such, the storage capacity of Faradaic pseudocapacitance is limited by the finite quantity of reagent in the available surface. A Faradaic pseudocapacitance only occurs together with a static double-layer capacitance, and its magnitude may exceed the value of double-layer capacitance for the same surface area by factor 100. Depending on the nature and the structure of the electrode, because all the pseudocapacitance reactions take place only with desolvated ions, which are much smaller than solvated ion with their solvating shell. The amount of pseudocapacitance has a linear function within narrow limits determined by the potential-dependent degree of surface coverage of the adsorbed anions. The ability of electrodes to accomplish pseudocapacitance effects by redox reactions, intercalation or electrosorption strongly depends on the chemical affinity of electrode materials to the ions adsorbed on the electrode surfaces, well as on the structure and dimension of the electrode pores. Materials exhibiting redox behavior for use as electrodes in pseudocapacitors are transition metal oxides like RuO2, IrO2, or MnO2 inserted by doping in the conductive electrode materials such as active carbon, as well as conducting polymers such as polyaniline or derivatives of polythiophene covering the electrode material. The amount of electric charge stored in a pseudocapacitance is linearly proportional to the applied voltage. The unit of pseudocapacitance is farad. Potential distribution. Conventional capacitors, such as ceramic capacitors and film capacitors, consist of two electrodes which are separated by a dielectric material. When charged, the energy is stored in a static electric field that permeates the dielectric between the electrodes. The total energy increases with the amount of stored charge, which in turn correlates linearly with the potential between the plates. The maximum potential difference between the plates is limited by the dielectric's breakdown field strength. The same static storage also applies for electrolytic capacitors, in which most of the potential decreases over the anode's thin oxide layer. The somewhat resistive liquid electrolyte accounts for a small decrease of potential for wet electrolytic capacitors. While electrolytic capacitors with solid conductive polymer electrolyte, this voltage drop is negligible. In contrast, electrochemical capacitors consists of two electrodes separated by an ion-permeable membrane and electrically connected via an electrolyte. Energy storage occurs within the double layers of both electrodes as a mixture of a double-layer capacitance and pseudo-capacitance. When both electrodes have approximately the same resistance, the potential of the capacitor decreases symmetrically over both double layers, whereby a voltage drop across the equivalent series resistance of the electrolyte is achieved. For asymmetrical supercapacitors like hybrid capacitors, the voltage drop between the electrodes could be asymmetrically. The maximum potential across the capacitor is limited by the electrolyte decomposition voltage. Both electrostatic and electrochemical energy storage in supercapacitors are linear with respect to the stored charge, just as in conventional capacitors. The voltage between the capacitor terminals is linear with respect to the amount of stored energy. Such linear voltage gradient differs from rechargeable electrochemical batteries, in which the voltage between the terminals remains independent of the amount of stored energy, providing a relatively constant voltage.